Thank you to the organizers. Madrid is definitely one of my favorite places on the planet, so I'm glad you guys had it here. I have to say, I've never given like a TED talk, so this is a little uncomfortable for me not having a podium in front of me. So at Hopkins, we usually have our nice little podium and our microphone stuck to that, so we'll see how it goes. So I'm going to talk about frailty and resilience a bit differently than Leo did. I want to start out by saying, though, this morning the sessions were really, I think, highlight the great basic aging biology that has flourished over the last 20 years. And it sort of, I think, represents kind of a bookend to this great story of aging and how we're trying to meet in the middle between clinical care and basic science. And I think we started from the opposite end as geriatricians, sort of taking care of older people, trying to figure out why it is that they're sort of falling apart late in life and kind of moving more and more into physiology and biology. And hopefully we're getting closer to meeting in the middle and coming up with some good solutions. So here we go. So there are really two goals, I think, for geroscience, for clinicians, really to promote resiliency, function, and cognition in older adults. That's what we try to do all the time as a geriatrician, and reduce frailty and the accumulation of chronic diseases. So those are kind of the big picture of what we try to do. This is a nice figure that was published a couple years ago that shows sort of the lifespan of people in the U.S., with most people sort of dying at these days in the sort of late to early 80s. That's sort of the peak death time. And the functionality sort of starts really changing after 70. And as geriatricians, we really notice between 70 and 80, there's often a steep drop-off, increase in falls, increase in problems with driving. That's probably getting pushed out now. Even in the last decade, it seems to be sliding a bit in this direction as more people exercise and are at least conscious of things that they can do to improve their health. So again, our focus is often on really trying to move this red zone further out. Certainly people want to live longer, and if they're healthy and living longer, then that's a great thing as well. This is another figure that shows the sort of these three phases of life that we heard about earlier today. Older age groups are the ones, again, that geriatricians most often take care of. And I have to say, people in this age group often they're not ready to die. They really want to keep living. They want to do things, maintain their independence, and really continue to contribute to society. And sort of this is almost like a third age where people can figure out what to do and have the life where they're not raising kids and working like crazy and can do things and give back to society. So if we could pick this curve up a little bit, this sort of functional decline that sort of starts here in midlife, then older people would be more likely to be able to do that. As a geriatrician, we often, geriatrics doctors often focus really way out here on the end, and most often people who are not robust, rather frail, and have a lot of medical problems. And as I've moved along in my career, I certainly realize that probably the time to most impact this curve is way back here. We're not going to pick these folks up much. But if we start changing some of the paradigms of treatment and thinking about interventions here, then I think we'll better serve our patients. So this is a picture of my great uncle and my great aunt. This is my grandfather's brother and his wife. He unfortunately died about a month ago at the age of 97. She's 99 and doing very well. And I interviewed them a couple years ago, and this is sort of what they want. High energy levels, good health, living independently, clear thinking, and having good social contacts and meaningful activities. So as people live into their 70s, 80s, and 90s, I think this is a good way to think about it. The other thing I wanted to illustrate is with this couple is the differences on how they got to be this age and how they got to be healthy. So these were taken, this picture was taken, I think she was 95 or 96, so maybe about two or 3 years ago. So you see that their diet is horrible. So, sorry, Anna Maria, she there's hope for you. Look, she drinks only Coke her whole life. And she doesn't like vegetables. She just never has liked them. But she's 99, and her father lived to be 106, though, so she's got the genes. And he always said, well, I don't have any of those genes. People die relatively early on my dad's side of the family. And he said she just kept pulling him out of the grave. Every time he got sick, she would reach in and pull him out. But he was one who actually had a relatively healthy lifestyle. He never smoked. He was outside all the time, very physically active, and he ate relatively well. So there are different ways to get to healthy aging, and I think as we move through this field, we're going to have to be thoughtful about these precision approaches and different measurements that can pick up on potential deficits as people get older. So I'm going to talk about the human models that we use in geroscience discovery, biologic characteristics of frailty and resiliency in new directions. I'm not going to really include any data in this. But first, physical frailty, as Leo mentioned, there are lots of constructs of frailty, but the one we've used is the Fried Frailty Index or phenotype, and we've kind of moved to calling it physical frailty at this point because it uses a number of physical function measurements to calculate it. But really, we've defined it as an age-based biologic change in multiple molecular and physiologic systems that provide a platform for vulnerability. So frailty and vulnerability are one and the same. And changes likely persist for years before manifesting in clinical signs or symptoms. So these things are happening at low grade and even at everyone sitting in the room at this point. The construct we've always used is that it's a deeply biologic construct with these sort of signs and symptoms emanating from changed biology, and some of the strands of what we've heard today certainly consistent with that. This is an old figure that I like to start out with and kind of say we started out here trying to figure out what frailty was, just to give it some definition, and we know if we find frail people, they're much more likely to have these adverse outcomes and die early. So say there's a room full of 80-year-olds and the 15% are frail are going to have these bad outcomes happen to them at much higher rates. The syndrome we defined as physical syndrome of frailty, and through probably hundreds of association studies, epidemiologic studies, we sort of found the major correlates of physical frailty and have started working on the molecular genetic pieces back here, and we heard a lot about that this morning. And hopefully through these science initiatives, more and more of this will be integrated into it. Certainly disease states have to be taken into account in anything we study in older people and these human models because they're certainly playing a role in this physiology and probably even in this biology as well. So these can't be ignored as we begin to deal with human subjects. This is a bit more complex model, the same kind of linear thinking, but I think it's helpful in developing hypotheses and things to test, but also to keep in mind how complex frailty is in this sort of aging state of vulnerability. And as we work backwards and try to prevent this, I think some of these tenets will be helpful. So again, bad things happen to frail people. We know what it looks like. It's clinically apparent when people get there. The physiologic realms that we think are important are chronic inflammation, HPA axis activity, sympathetic nervous system. So in general, sort of stress response systems being activated. Energy production goes down, and we'll talk a bit more about that, and then a lot of hormonal alterations. We heard a bit about the growth hormone. But if we had to summarize all of the physiologic, epidemiologic studies have been done, this probably best characterizes them. This morning we heard about potential aging triggers, and I would put mitochondrial decline and sort of linking that to inflammation and energy production at very much at the top of the list. So I put it at the top of the list. There are other things that certainly play a role. We heard about senescent cells. It certainly could be driving inflammatory pathway activation, changing energy production, autophagy certainly playing a role in some of these physiologic pathways as well. But again, in the human condition, you can't remove the genetic variation that we know plays a role. Environmental conditions play a huge role, so smoking, lack of exercise, dietary changes, this certainly plays a big role and can drive this, also driving some of these biologic changes, maybe earlier mitochondrial decline, for example, or autophagy-related changes. And then diseases, I've listed many that are associated with changes in this physiology, so I often think of people who get to frailty, physical frailty earlier as certainly having this aging-related trigger that brought us together today, plus lots of diseases that may or may not be actually triggered by these aging-related changes. Throw some genes and a bad environment in, and they get to this pathway earlier than other people. But I think sooner or later, most people are going to get here. It might be through some primary aging mechanism or mostly a disease mechanism, but on almost everybody it's a combination. This is just another way to look at it, and again, these models have been helpful for us to kind of pick apart specific changes that we observe and try to study them in more detail and try to make relevant to at least the clinical practice some of the changes that the great basic biologists are discovering. So around here we mentioned mitochondrial changes, cell senescence, stem cell exhaustion, for example. And then up on a physiologic level, I would say these are the two major domains that we have found related to frailty with altered stress response systems. And I talked about them, inflammation, an innate immune system, really, HPA axis changes and autonomic nervous system activation. And then this energy metabolism, sort of probably driven by mitochondrial changes, and also glucose metabolism changes are certainly a very primary component of what we call physical frailty. And I think linking back to what we heard this morning and trying to figure out more of the basic biology that's driving this physiology is going to be critical in moving the field forward. Up here we have this clinically apparent level, what we see in clinical practice. So if somebody comes in the office and are frail, we don't see this stuff, and we don't really have any tests at this point to measure it. They might be glucose intolerant, but and we could pick that up through some routine lab tests. But things that we often see, again, are these complaints of fatigue or low energy, a little bit of weight loss, muscle weakness, and then some labs that we can get sometimes that we pick up signs of frailty are listed here as well. So again, in summary, for the physical frailty, it's complex, multifactorial. It's got both molecular changes, and these probably alter the physiologic systems, and I think there's a huge amount of work that needs to be done to help connect these two areas. I think that if I had to summarize the major physiologic systems, energy metabolism, both glucose metabolism and mitochondrial energy production is way, way, way up at the top of the list as what might be driving frailty. And figuring out what's causing those changes early on could be critically important. And then these kind of unraveled stress response systems, so things like chronic inflammation that gets turned on and never gets turned off. The same with HPA axis activity. Over time, these things, I think, drive the physical frailty as we know it. And I think it's been very informative for the resiliency research that we've embarked on in the last few years. We know resiliency is different than frailty. It can be thought of as the flip side, but often you can't really see resiliency as you can see frailty in clinical practice. And that's in part because you need a response to a stressor. Really, the individual has to be under some kind of stress to determine whether they're resilient or not resilient. And in order to have that, you need some kind of phenotype that has or an outcome that has wide variability. So we've used things like knee replacement surgery or bone marrow transplant, where some older people get them and they do very well. They go home very quickly and don't have any pain, for example, whereas others don't recover quickly. They don't ever get back to walking in a normal fashion. They have a lot of pain. So those are sort of resilient versus non-resilient outcomes. So you need something like that to find it. And then use of static and dynamic measures probably will help capture these various strands of biology that I think are going to be important to better define what resiliency is in human subjects. So a couple of years ago, we were fortunate enough to land a grant to help us study physical resiliency, and this is sort of the model that we use. And this, I think, ties together both the physiology, the basic biology, and this sort of clinical practice paradigm that we've used to begin to try to unravel what resiliency is in older adults. So I'll walk you through it. So stressors. So we know that people have to be stressed in order to see what their outcomes are, to see if they're resilient or not resilient. So those are our outcomes. Stressors, in this case, are clinical stressors, bone marrow transplant procedures in older people, which are a pretty big stressor. Renal hemodialysis, new dialysis within the first week of initiation, and knee replacement surgery. And so all three of those have big differences in outcomes. So again, take a room full of 70-year-olds. About a third of those 70-year-olds will survive the bone marrow transplant and do great. About a third will die relatively quickly, and about a third kind of live in this intermediate status with cognitive decline and physical function decline. So we see a range of outcomes, for example. And so the model that we put together basically is trying to capture a number of measurements before, during, and after the procedure so that we can then relate them to these resilient or not resilient outcomes. So the baseline determinants, we know age and psychosocial behavior, disease states will matter. But on the molecular side, measures of senescence, epigenetics, biophysics, and I'll talk a bit about that in a minute, have been incorporated to see if we can determine that. So, for example, if people have a lot of senescent tissues around their knee, if that's going to matter in their recovery. Then we collect a number of things around function, fatigability, and then many of those physiologic variables that I talked about in frailty to see how those are impacted before, during, and after the procedure. A couple things that we've put in there as well. We're trying to find surrogate measures of resiliency, so things like the frailty phenotype. If somebody's robust in our frailty phenotype, then we would at least hypothesize that they're going to be resilient, and if they're not, if they're frail, then they're going to be not resilient, for example. And then a number of dynamic stimulation tests that we do before. So glucose tolerance testing, ACTH stimulation tests, autonomic nervous system testing. So we try to probe those systems before people have to actually have their stressors to see if we can pick up some biologic signals that might predict outcomes. So that's our model. We don't have a lot of data. We just started, we're finishing a pilot phase and about to ramp that up. So in a couple of years, hopefully we'll have some great data. It's another kind of messy homemade slide that, again, shows these big domains that we're trying to capture that we think are important in this, both in resiliency and in frailty. In the interest of time, I'll just kind of fly through this. But again, the major stress response systems, again, and I think an area that needs further study is really in the physiologic domains. And here, chronic innate immune system activation, sympathetic nervous system, renin-angiotensin system, and HPA axis, they all are actually linked. And there's some hypothesis or some evidence that if you calm one of these down, the other ones will calm down as well. Or if one of them gets activated, they tend to drive the other ones, and you end up with these very activated stress response systems in a subset of frail older adults that then lead to a number of mediators that probably drive things that we see in late life, chronic depression, anxiety, organ and tissue specific changes, fibrotic changes, disease states, and disability through muscle decline. Another thing that we've been working on that I think could potentially be important, it's really not in the deep biology domain, but more in the physical properties of cells, and working with some bioengineers at Johns Hopkins, we've made a little bit of progress, and hopefully we'll have some more moving forward. But this was a study that was published a couple years ago. And basically the idea was to look at fibroblasts and human fibroblasts from healthy donors in a wide variety of age groups, and measure a number of parameters, both biologic parameters and physical parameters. You see here things like cell morphology, traction strength, cell stiffness, cell motility. And basically what came out of this is that the physical properties of the cells were actually more associated with age than some of the biomolecular properties of cells. So there's a pretty good correlation, especially with things like cell motility. These were fibroblasts in dishes and measured. It was very close to what we're seeing in age, but also the morphology and shapes of the cells, and especially the nuclear membrane. So again, a biophysical property that predicted age quite well. So we're doing some further work on that, and it may have some relevance to gene transcription and some changes, age-related changes in pathways that lead to these physical properties. But so in closing then, the considerations for future research, geroscience action, I think, is at the intersection of this basic biology and physiologic systems, and Felipe certainly alluded to that earlier. There's a lot of potential connections, I think, still big question marks that will help pull the fields together in the future. There's not going to be any single pathway that we can identify, I think, that's going to predict who's going to get old. There's going to be some differences between individuals, or between get frail or stay resilient. And I think these detailed physiologic studies that connect molecular aging to physiology are few and far between and need to be increased. Again, this kind of reminds me again of that the need for more precise approaches, and I put that here as one of my major bullets here as we move further and find great measurements that help us predict aging-related conditions or declines. I think if we have a specific panel of biomarkers that we can say, yes, this person has chronic inflammation and a lot of senescent cells and needs this particular treatment, or this person has cortisol abnormalities and autophagy changes, then we could push in that direction, for example. So those are things that I think we need to move forward with, because I think one shoe isn't going to fit all sort of anti-aging or anti-health span treatments. And this is a huge amount of work done with lots of different people. The highlighted folks are probably major thinkers in this area with us, and then our Biology of Healthy Aging team that does a lot of the lab-based work that we work on. So thank you.